This illustration deals with conductor to be grounded. And we're talking about AC systems in accordance with 250.26. Now, I would like to point out that 250.26 is used in conjunction with 250.20 A and B. Remember, 250.20A1 dealt with where you would have to ground low voltage systems of less than 50 volts, or you wouldn't have to ground them. 250.20B said if you use a transformer in the manner that's listed here, you have to pull the grounded conductor to the service equipment and ground there. Basically, you're grounding the transformer. You got to bring that grounded conductor in for an effective ground fault path, like on 277-480, even though you only had three-phase equipment and you set a main and fed a separately derived system and stepped the voltage down to 120-208, basically. That's what we're talking about. Now notice again, to the left at the top, I can pull one hot and one ground. Now that it could be a neutral, but it's called a grounded conductor because it's not pulling unbalanced current. It's pulling exactly the same current as your L1. Now, so just one grounded conductor with L1. I couldn't pull two L1s with one grounded conductor and double it in size. That would be prohibited by 250.26. Now over to the right, I have a three-wire system. I have a 240-volt coil tapped in the center, and it's a neutral. It carries the unbalanced current. Again, I'm a little repetitious here, but I have to look at it. Maybe you just looked at this illustration only. So if you had L1, 100 amps, L2, 80 amps, and neutral, C is 20 amps. But if you had, say, 90 amps on L1, 90 amps on L2, there's no unbalanced current. The neutral would see zero, which would be great if you could do that. Now, the next illustration is a Y to the left. And notice it's a Y system, and you can pull three hots with one neutral. The previous illustration to the right that we just looked at, you could pull two hots with one neutral. But that's it. You couldn't pull three hots with one neutral from the same phase, or two hots with the neutral from the same phase. In other words, you'd have L1, L2 neutral, L1, L2 neutral. That's what I'm trying to say here. But now notice that Y system you see right in the center there, of the grounding loop and the transformer above it, single phase. It's a Y, and you have to worry about harmonics. So if you have harmonics, nonlinear loads, double it in size. Or you have to have a K-rated transformer to allow for that. Now, you can pull three hots with one neutral. Now notice to the right, you have that closed delta. You have three windings. Notice there are two 40-volt windings each. You have three 240-volt windings. You've tapped one of them in the center. It's a common tap point. And you get 120-volt from L2 and L3 to the neutral. But from any L1, L3, and L2, you get 240-volt. But notice that high leg, L2, is going through a 240-volt coil, 120 to the left. To the right-hand side, and using that coil, you're going through 240 to 120 to ground. And as I said earlier, 240 plus 120 divided by 1.732 is 208 volt. And typically, that's the high leg. Now notice all the sections that you have to look at to really get a good feel for that high leg and what's required. Look at the grounding loop. You really start with 110.15. And that says it's got to be orange in color, or it's got to be identified in a identification manner that's acceptable to the authority having jurisdiction or the utility. And some utilities used to let that high leg be red, and that's why they called it the red leg. Some people called it a Y leg. Others, high leg. So Usually those three names, one of them catches it, but by code it's a high leg. And then notice next, if it's service, it's 230.56 because you're service. And then you'd look at 408.3E, 408.3E, informational note, and 408.3F1, it basically says, it's got to be the center. But notice, you only have to identify high leg when the neutral's involved. That's what's important. And if you don't look at all them sections, you might miss that. And you might identify it. You'd say, is that wrong? No. But remember, it has to be the center leg, the B leg, L2. So keep that in mind. Now your grounding loop starts 240.22, 1 and 2. 430.36, 430.37, and 430.32A1. Now those are loops involving a corner grounded system and high leg. So this kind of gives you the information that you need to know. Then at the bottom, notice there that we're actually grounding one of the ungrounded phase conductors. And that sometimes shakes up an electrician that's not used to this type of system. I was very fortunate in one manner. In my electrical career, in the Metroplex area, you're going to see all these systems. The utility won't give you hardly any more at all delta. They'll give you a Y, and you'd have to set a delta transformer. They want everything balanced as good as possible back to them. So you'd have to check with utilities on that. But if you have that transformer at the bottom, right above the caption, grounded to be grounded AC systems, there's your sections that regulate it. And you can fuse it like at a fusible disconnect for an irrigation pump. You could fuse it if you provided overload protection in accordance with the sections that you see there. Or you could have a 3-pole breaker that would disconnect it. But you've got to follow the rules to 240.22, 1 and 2, along with the other sections that you see there for that type of system. Now, I believe that this illustration, 16-30, will illustrate the conductor to be grounded when you have an AC system in accordance with NEC 250.26.